Did you know? We live in a world powered by technology. But have you ever wondered what it takes to produce the devices we rely on every day? The powerful microchips in the gadgets are built using semiconductor. In 2019, 32.4% of the semiconductor market segment was for networks and communications devices. In 2021, the global semiconductor market is foreseen to hit $469.4 billion and the semiconductors annual growth rate is predicted to be 8.4%, and it is projected to reach $726.73 billion by 2027. Semiconductors are crafted from a variety of raw materials, including silicon, germanium, gallium arsenide, and indium phosphide. Among these, silicon stands as the most widely used semiconductor material because it is the second most plentiful element in the Earth's crust and forms a strong, diamond-like crystal structure, making it durable and reliable for electronic applications. These materials undergo processing and purification to form wafers, which are the foundation for semiconductor devices. Semiconductors are classified into two types: intrinsic and extrinsic. Intrinsic semiconductors, like pure silicon and germanium, have a natural balance of electrons and holes, meaning they aren't very conductive at room temperature. But what if we could enhance their conductivity? That's where doping comes in. During doping, the specific impurities are introduced to transform intrinsic semiconductors into extrinsic semiconductors which have greater conductivity. However, the conventional semiconductor production lies a hidden environmental cost, which is acid waste. In semiconductor production, etching process is the most harmful step. Based on research, the composition of the acid waste depends on the reaction conditions of etching process in semiconductor, which generally consists of 30 to 40% nitric acid, 7 to 12% acetic acid, 10 to 25% hydrofluoric acid, and 1.5 to 2.5% silicon. Why nitric acid and hydrofluoric acid hold the biggest composition? This is because hydrofluoric acid is widely used in the etching processes and for cleaning wafers. According to the Semiconductor Industry Association, waste solutions of hydrofluoric acid account for more than 40% of the hazardous substances produced in the semiconductor industry. Besides, nitric acid is also commonly used in combination with hydrofluoric acid in order to control the etching rate. So, what are the impacts of hydrofluoric acid and nitric acid towards human and environment? Let's take a closer look. Hydrofluoric acid and nitric acid are highly corrosive acid. Therefore, excessive hydrofluoric acid in waste solutions will cause bone disease that caused by excessive fluoride accumulation in the body and tooth spots due to fluoride affecting enamel formation. Plus, nitric acid will cause chemical burns and blindness, and if nitric acid is inhaled as a mist, it will cause mucous membrane damage. For example, the membrane of bronchi and alveoli of lungs will be damaged. The acid also contributes to acid rain, which damages ecosystems by degrading soil quality and affecting aquatic life in oceans. To overcome the problem, Area Selective Atomic Layer Deposition (ASALD) has been developed. ASALD is a bottom-up fabrication process that starts with bulk wafer, in which thin film materials are chemically deposited onto selective areas of a large wafer's surface. The area covered with thin films is known as a growth area, while the area where no chemical reaction occurs is called a non-growth area. The process starts with the introduction of a precursor. It is a special chemical compound that carries the material to be deposited. The precursor reacts only with the growth area, forming a thin atomic layer. Any excess is removed to prevent unwanted reactions. Then, a second precursor is introduced, completing the reaction and forming a stable layer. By repeating this cycle, the thin film grows layer by layer with extreme precision. Controlling the number of cycles allows manufacturers to fine-tune the film's thickness at the atomic level. With ASALD, thin films are deposited only where needed, reducing the need for etching. The acid waste that is largely used in the etching can be reduced and its negative impacts mentioned earlier can be avoided. Fewer etching steps in semiconductor manufacturing mean using less etchant and chemicals, needing fewer protective coatings and masks, thus lowering material costs. These impacts directly contribute to achieving Sustainable Development Goals (SDGs). By reducing the number of steps in material used, SDG number 9 is achieved since a more sustainable and foster innovation ASALD is used. SDG number 12 is also achieved since generation of pollutants and waste is reduced and fewer processing steps mean less resource consumption. Additionally, ASALD is possible at deposition temperatures as low as 60 degrees Celsius. Implementing low-temperature deposition techniques reduces energy consumption, prevents damage to the sensitive wafer-based materials, and lowers operational costs. These positive impacts achieve SDG number 7, which ensures access to sustainable, reliable, and efficient energy system. Besides, precision of ASALD also helps prevent edge placement errors, EPES, making devices more reliable. In conclusion, ASALD serves an eco-friendly alternative that supports greener, more sustainable semiconductor manufacturing.